All right. Hello. Today I'm joined with Alex Pexi, Kiri Linda, and myself, Bailey Bouchard, to present our proposal for the prioritization and distribution model we have created to for vaccine orders during COVID times. Our model was created by ourselves with the help of Robert McElhaney and Hayden Sanowski.
All right, so an introduction to the problem is that Gavi funds immunization efforts for numerous low-income countries around the globe. UNICEF is the entity that's in charge of procurement for those vaccines and the delivery of the vaccinations. So there's a challenge of scheduling and routing flights during COVID, especially as the transportation capacities tend to drop. And this is seen throughout the year in certain situations, but it's really was seen a lot during COVID. So our model seeks to handle that situation and prioritize which order should be sent. So some more background is that vaccines are essential for the health of low-income countries. Um, Different immunization campaigns include routine campaigns, outbreak campaigns, and supplementary deliveries, each targeting kind of a different sort of disease in the country. The UNICEF logistics unit maintains a list of flights and basically quantities that can be shipped. Um, but during COVID-19, UNICEF was forced to create a new approach for optimizing its orders as transportation capacities dropped. So over to the right, you can see the graph of transportation capacities, and you can see the real steep drop around April, where the shipments were kind of at an all-time low, and this model became a really integral part of UNICEF's delivery system. So understanding the problem is that vaccine delivery to low-income countries is planned for all 52 weeks. There's a big list of orders. There's a large list of vaccines and countries that need to be delivered to. And starting in week 11 is when we see that drop in transportation capacity, specified in the graph in the earlier slide. So not all of our POs can be delivered. So we need to have a means of assigning which purchase orders are delivered and which purchase orders are delayed. The way we choose that is different considerations for each country. Some of those include effectiveness in using the vaccines, and the ability to store the vaccines after they're delivered to that country. Another one is current inventory levels for the vaccines at each country. And then the last one being the current coverage for each country for each vaccine. The amount of the population that's already received the vaccine is going to influence our decision to send that country an order. Considerations for each purchase order include the number of doses in the delivery, the current status of the order, whether or not it's past due, and the target of the order, whether it's targeting the outbreak or the routine delivery. So the goal of our model is prioritize, model, and solve. So the prioritization piece of our component will prioritize the orders. The model component will take those priorities and determine which orders are the most optimal to be sent. And then the end solution is the integrated package of those two pieces that can be deployed by UNICEF each week. So we'll start with the prioritization model. So understanding the prioritization, there's really two key pieces here. It's the criteria for decision making is based off of 6 main factors for us. So there's multiple criteria for deciding which purchase orders are going to be the most important. And the struggle there is to compile those 6 criteria into a single priority index or some sort of objective function so that our model can choose which to send. So the different alternatives we have for determining those priorities are really what makes our model strongest. So a few of our alternatives that we looked into were analytical hierarchy process, AHP, multi-criteria optimization, and data envelopment analysis. Each alternative provides a different way to deal with the multiple criteria. And we'll get into why we chose what we chose and how it helped us. So the criteria we have for our priorities are the ability to use for that country, how effectively can each country utilize their vaccines, the inventory on hand for each vaccine at each country, the current status, kind of where are we lacking and where is there surpluses that we can take advantage of, the number of doses in each purchase order, the kind of what we're trying to force into the country, and then the type of the purchase order, again, the routine vaccination or the campaign vaccination. The existing coverage, how many people in that country are already vaccinated, that's going to be a key factor for us. And then the weeks delayed. So if a week is, or if a PO is delayed by a few weeks, it's going to be more important because we can't delay POs for too long. So why is AHP the best? Like we were saying, the priority index is kind of our goal here at the top in blue. And what AHP does effectively is integrate all 6 of our criteria into that one priority index. So global weights reflect the importance of each criteria to the overall priority index. And then down below, our local weights reflect the importance of each purchase order within the given criteria. So each purchase order will have a local weight for each of our 6 criteria, and that local weight would be calculated with respect to how important is each purchase order in comparison to the rest. And then again, the single priority index is kind of a key thing for us, as instead of working with 6 factors, we're now working with one priority index.
So here's our mitigation plan for some of the disadvantages that may come with using the AHP. AHP relies heavily on the availability of reliable and objective data to inform the decision-making process. However, in the case of vaccine prioritization, there may be limited data available on the factors. AHP requires input from stakeholders as well. However, in the case of vaccine prioritization, there may be limited time and resources available to gather input from a diverse range of stakeholders. Vaccine prioritization decisions need to be made quickly and efficiently. AHP can be a time-consuming process requiring significant time and effort to gather the data, establish criteria, and calculate weights and priorities. AHP does not explicitly consider uncertainties and risks in the decision-making process, which can lead to suboptimal decisions and outcomes. AHP also relies on judgments and opinions of the decision makers. If the decision makers have different opinions or biases, it can lead to inconsistent or inaccurate results. So before we created our entire global matrix, we ranked our criteria using AHP calculator. This was done by inputting how important we thought that each criteria was compared to each other criteria. And this gave us a specific number, which was then ranked. As you can see, number 1, we have ability to use. That was our most important one. Number 2, existing coverage. Number 3, weeks delayed. Number 4, the number of doses. Number 5, inventory. And number 6, purchase order type. At the top of our criteria was effectiveness. Above all other criteria, we have argued that if a country has a poor ability to utilize vaccines, it should be given a lower priority. If any order is delivered to a country that has poor utilization of the vaccines present, it may be possible that the order is not able to be effectively distributed while outside help is limited due to the COVID-19 restrictions. Thus, we have reasoned that countries that can make use of their vaccines at a greater independent level should be prioritized higher than those that cannot for the time being. Our second one is coverage. We have rated the coverage criteria as the second most important criteria. This is because the higher the coverage, the more people are protected from the disease, reducing the risk of outbreaks and epidemics. Therefore, if there is a higher coverage, it could be deemed less important to send the purchase order. However, if the country's coverage of that vaccine is low, it would be significantly more important to get the vaccine purchase order delivered. Low coverage areas are often more vulnerable to outbreaks or infectious diseases due to lower levels of immunization. Delivering vaccines to these areas can help prevent the spread of disease and reduce the risk of outbreaks and epidemics. This is why it's the second most important. As our third most important criteria, we have put weeks delayed. We wanted to ensure there was an emphasis on orders not being delayed far past their initial date. In order to ensure this was a hefty comparison, delays in vaccine delivery can impact the timeliness of vaccination programs. When there are delays, it may take longer to reach the target coverage levels, and the benefits of the vaccination may be delayed. In some cases, timely vaccination may be critical, such as during outbreaks or in situations where the disease is spreading rapidly. Delays in vaccine delivery can also impact the logistics and planning of vaccination programs. When there are delays, it may be more challenging to plan for vaccine distribution and ensure that the vaccine is administered efficiently. The amount of doses per order was rated as our fourth highest criteria. This was rated only slightly behind the weeks delayed criteria. This is because we felt the higher the number of doses that were in the order, the more important it would have compared to if there were a very small number of doses in the order, which would have less importance. Vaccines are typically administered in 2 or more doses, and receiving the full recommended dose series is essential for achieving the maximum protection against the target disease. If there are fewer doses per order, there will be fewer people who can be fully vaccinated, and this could compromise the effectiveness of the vaccination program. The existing inventory of a country is not as important as the number of doses in an order because it is possible that the existing inventory may not have the same antigen or vaccine type that is needed to address a particular health concern. Additionally, the existing inventory may not be sufficient to cover the needed doses or may not be stored properly, which could compromise their efficacy. On the other hand, the number of doses in an order indicates the exact amount needed to address a particular health concern and is a more accurate measure of the actual need. Therefore, prioritizing orders based on the number of doses needed can help ensure that the right amount of vaccines is delivered and that they are appropriately stored and administered to those who need them. And our final criteria is the routine versus campaign. We have rated the criteria as our lowest. We have reasoned that UNICEF would only be conducting a campaign for vaccination under the assumption that the existing coverage for a specific antigen was low, and thus, despite the importance of a campaign specifically, the rating of its coverage would be considered of much greater importance. A campaign conducted in an area with high existing coverage in comparison with a campaign conducted in an area with low existing coverage should reflect a much lower score. This idea, coupled with the low prevalence of campaigns compared to routine purchase orders, made us rank this as the lowest of the criteria.
So based on the following the previous reasons that Kyria had just discussed and our own ranking from 1 to 6 of how we viewed each criteria, we were able to create the following AHP matrix to see how these compared to each other in terms of their weights. And the decisions and the reasons we had given before were responsible to how we assigned the values throughout this. So given that effectiveness we decided would be the most important and the routine versus the campaign criteria would be the least important, that has obviously the highest value between the rest of these. And the rest of the values were also given with the same amount of consideration in mind. Using the first code of our model, we were able to sum across the rows of that AHP matrix and then divide each element of that row by that summation, and then take an average of the column provided in this matrix to get the global weights for each of our criteria. Obviously, as we have in the bottom here, it's showing that this is being done automatically by code and isn't something we would need to revisit later on the line. And proven from our AHP, our matrix before it, you can see it's still ranked in the same manner. Most important at 40.7% is the ability to use, 25.2% for the existing coverage, 17.1% for the amount of weeks delayed, and 7.2 for the amount of doses per order present, 5.7 for the existing inventory, and then lastly 4.2% for the type of the purchase order. Now that we've actually compared how the criteria are to each other, we need to look into the alternating purchase orders and rank how these criteria compare to each other within themselves. And if you're wondering what that means, that's if and essentially we were able to go through it by we took data available to us for the immunization coverage country disease file and the prioritization sim data provided to us through UNICEF. And we had created a separate master Excel sheet that we titled Weekly Vaccine Inputs, AHPY. And this Excel sheet has based on a PO number from 1 to 1,524 based on the amount of purchase orders for each country and vaccine present. In our model, in order to properly a bit of manual legwork is required for how we've set it up, that you will have to filter out all weeks except the specific week that the model is being run for. So as our proof of concept, we started at week 11 and filtered out everything except that. And we created a new file from all of the data present in that, entitled it week 11. In this case, as we're instructing, it would be week n, where n is the value of the current week being evaluated. It could be week 11 through 52, essentially. So the way we actually compared the local weights was from reading the week 11 file, we were able to rank in a ratio between 1/4 to the highest value of 4 um, to obtain our values. And we said we would prioritize the ability to use the highest ability to use would have the highest prioritization present. And this can be present by taking if one country for one purchase order is only able to use at a rate of 4, which in this case was rated at the lowest, and the highest was rated at a 1. If we take a ratio between these values, then it should return the highest value present and be able to place it in this pairwise comparison matrix. If you looked at order 305 compared to 303, it is one of such order like this. It is saying that order 305 is able to use they're able to use their vaccinations within totally independently and at a much better rate than order 303 would be able to use theirs. In terms of coverage, we stated that countries that have a lower coverage should obviously be more important than those that have a higher coverage. Similarly, we created a ratio between coverages present in order to find this. And there are many countries that for purchase orders they had, there was no existing data to show if they had any coverage present during this. For all orders where this was the case, and they did not have an existing coverage, we assumed that it would be equal to a value of 0. To avoid dividing by 0 as an error for this specific criteria, instead of setting values of 0 specifically, we would set it as a value of a very minuscule number. So maybe 0 repeating 5 times, followed by a 10,000th in the decimal place. As a result, if you look at the code, values that would be greater than 100th or 1,000th, those will return the value of 9 when you're dividing by another smaller value. For our weeks delayed, it was the only criteria where we realized instead of taking a ratio, it would be more important to take the difference between the amount of weeks delayed in a purchase order. The way we've ranked it is that essentially by each increasing week, the priority should shift up a value of 1. We thought maybe we could have it in a range, but we think that for we believe that the larger orders in general are going to be the ones that would be delayed to begin with. And to ensure that they can eventually be delivered and quit being delayed, the value should drastically increase. Where in this case, after an 8 weeks difference between two orders, the 8 weeks difference would have the highest priority, and then decreasing go from 9 to 1. When comparing the doses per purchase order, we said we would prioritize a larger amount of doses present in the order, which might seem strange as we wouldn't be able to get as equitable access. But our reasoning for prioritizing the larger orders rather than small orders is that the large orders are going to be the orders that are delayed in the first place. If our global transportation capacity is limiting greatly, and if we were prioritizing smaller purchase orders, it would still be easy to reach out to them. It's the countries with a larger population and a larger it's countries with a larger population that would be suffering and not those with the smaller one. For existing inventory, similarly to coverage, we had said that countries with a lower or a null set of inventory that they have already for their amount of purchase orders will be prioritized over those that don't have, or they do already have a existing inventory to fill their purchase order. Similarly to coverage as well, values that are 0 or values that are non-existent, we have set to a small minuscule value so that we would avoid dividing by 0 in this. Lastly, if we look at the type of purchase order comparing a routine versus campaign, we deemed campaigns to be more important than a routine as they reflected a low coverage and a need to quickly inoculate a large group of people, whereas a routine reflects a regularly scheduled vaccination. Um, the way we've done this again is once again through a ratio. And for when it's reading the week 11 or the weekend pairwise, the week master Excel sheet, excuse me, it's setting values of campaign as a variable where campaign is equal to 9 and a routine is equal to 1. This way, whenever you're comparing a campaign to a routine specifically, it always takes the highest priority over it. Whereas a campaign to a campaign will just be a value of 1, and a routine to a routine will also just be a value of 1. Something that is incomplete about our model is that we are supposed to have a third set of code that from the pairwise matrices from our second code file, which is reading from the weekend file, it should be able to read the output of these matrices and calculate the local weights for each criteria for each individual purchase order. As seen from the previous 6 slides, there is a separate pairwise comparison matrix made for each criteria. What we have to do for our model, as we were unable to complete our third code file in the time allotted to us, was manually calculate the local weights that result from these matrices. And we ordered this in terms of Roy G. Biv to show which order we would be doing this in. As you see on the left here in red, this is the resulting pairwise comparison matrix made from the code file. And there's going to be 6 of these made for each criteria. In order to calculate the local weight for any purchase order for any criteria, you have to sum across each row of this matrix and order that in a column as shown by orange. Then we take the matrix in red and divide it by this summation in yellow. And then in order to obtain the local weights, you then take a average of the column of each element in this matrix. And that's what we have in green, which this value in green is actually our local weights. But in order to read it, create an output for the optimization model to read, we've transposed this average over here. And then this is put into a separate file titled weekend priorities, or in this case, week 11 priorities, which is what it's looking at. From this, excuse me, that's not what's happened. That was the local weight. From this is put into a separate sheet where we can manually calculate the priority value of any. So once again, we have ordered this from Roy G. Biv, in this case, Roy G. If you look on our left in red here, this is showing the local weight for every order in week 11 for each of its criteria. So going across, if you look at order 349, this is its local weight for effectiveness, its local weight for doses, for the routine versus campaign, the coverage, the inventory, and then the delay. In order to calculate its priority value now, we need to multiply these values of the local weight by the global criteria weight for effectiveness, doses, routine versus campaign, coverage, inventory, and delay. This creates this matrix file on the right here in yellow. And these reflect the portion that is provided in the priority by each of these local weights. In order to get the priority value or the priority index of any single order now, we need to sum across for these. And this results in, on the right end on the green, which would be 349 is 0.03. And going down the list, this is the priority of any single order in week 11. From this, as our third coding file was not completed, this output here would be would be saved into a file that could be read in the optimization model as weekend priorities.
So now that we have the priorities, we can move forward and optimize which orders should be sent and which orders should be delayed. So with our optimization model, there's a few key assumptions. So number one is that transportation capacity for each country is calculated as a product of the number of doses planned to be sent to that country and the proportion of the capacity that's available for that week. Another key assumption for us is that if there's no planned orders for a country in a given week, then the capacity for that country is 0 doses. And then across all countries, that their transportation capacities are going to sum to our global capacity. A transportation capacity for one country may be used to send vaccines to another country. So if we're sending vaccines, if we're planning to send vaccines to one country, we can use that country's vaccine capacity to send a delayed order from the previous week if we need to. And then lastly, purchase orders will be sent in full. And when an order is delayed, it'll be delayed in full. So we won't be splitting up our purchase orders. So our optimization approach has inputs, decisions, and outputs. So as inputs, we have our global transportation capacity for each week. We also have the set of purchase orders that are available to be sent that week. So any delayed order from the previous weeks, as well as the new orders that are planned to be sent in that week. And then we'll also be reading the priority index that we just calculated in our priority model. And then we'll also be given the number of doses for each purchase order that is in that set of available purchase orders to be sent. The decisions we have to make are which purchase orders should be sent. And with respect to which orders we sent, we want to maximize the priority of all orders sent. And obviously we have to satisfy the constraint of global transportation capacity. We can't be sending more doses than we have capacity for. And then with the outputs, we need to read the delayed orders back into prioritization model for the next week. So our linear program as set up through Ample is containing what we just mentioned as our inputs. So our set is the POs that are available to be sent during the current week. Our parameters are the current week given through the model, the priority of each purchase order in that set P, denoted by small p, the global cargo capacity for each week, and then the doses of each purchase order in the set available. Then our variables are X, which is a binary variable. X takes a value of 1 if the purchase order is sent and 0 otherwise. And our objective will be to maximize the priority of P times whether or not that order is sent. So you can see if we send an order P, we'll be rewarded for sending that order with its priority. But if we do not send an order, X takes the value of 0 and that priority won't contribute to our objective. And then lastly, our last constraint there is to make sure that the total sum of doses we send is less than our cargo capacity. So defining the inputs. So as mentioned before, one of our inputs is the global transportation capacity for each week. So the way our code works is it's going to take the planned purchase orders for each country for each week, assuming that only what's planned is what our capacity is. Then the percentage of planned orders that can actually be received at each country each week will be multiplied by each planned purchase order to give a value of the number of doses that can be sent to each country each week. And then obviously compiling each capacity for each country, we are given a global transportation capacity. And assuming global capacity can be sent to any country, we can reassign cargo capacity from country A to go to country B, should country B's purchase order have a higher priority value. So defining the inputs continued is adding the data for Ample. So what our code is doing is reading the available purchase orders from the input file into a data frame. And then that data frame will contain all the planned purchase orders for the current week, as well as any delayed purchase orders. So that's defining our set PO for our model. Another input is to filter the data frame to only contain the parameters we need in Ample. So it simplifies our code so that Ample is able to read it more efficiently. And then last little bit is to read an Excel file to add the priority index of each purchase order to the data frame. And then as a result of this, we have our data frame that Ample can read from to receive all of those parameters. So our outputs determining which orders to send. So our Ample is integrated into AmplePy for our Python code, and our solver is Droby. So the priority is compiled into a singular index, which is an indicator of our objective. our global capacity is now compiled into a single value, which defines our feasible region. And knowing that orders are either sent or delayed in full, we can ensure that our variable X is binary. And then with all of our data in our data frame, the ample model can read through amplify and solve with Jurobi. So once we have our solution, we're able to output to a text file the values of X for each purchase order, which denotes whether or not that purchase order is sent. And through that, we can add our delayed orders to next week to denote that they're now part of the set available for that week.
File and our model currently loops at the moment. It starts with our Excel sheet, which we're of course filtering by the specific week that we are trying to create a priority for. From this master Excel sheet, and after filtering out the specific week that we're looking at, we create a weekend.xlsx file. We would already have run file number 1, which gives us our global weights for the 6 criteria. Code number 2 will be run, and it should be changed in the pathing and the name of the files that is reading and outputting to reflect that the current week that we are on. So if we're moving on from week 11, we're now on week 12, that will need to be changed in the code. This should then output code number 2 should then output a Excel file that would be called week 12 and have the 6 pairwise matrices. If our code number 3 was complete, it would then be run to read from this, from the outputs of 1 and 2, and then output the priority values that would be then read for our Amplify optimization model. The Amplify optimization model will give us the values of the orders that are being delivered and delayed. In order to be ready to optimize the next week, we would then have to take the weeks that are being delayed in that specific week, add a value of 1 to its delay column, and then change its delivery week to the next week that we will be optimizing for. From then, it should take over the same process. So if we just did this for week 12, we'll then filter by week 13 and carry out the same process. And ideally, this will be able to be carried out through the entire year or be able to pick up from any point in time following this pathing in the loop for the model.
So now I'm going to be talking about how we're going to integrate with the flight assignment module. The PO prioritization module will generate a list of prioritized purchase orders for the current week based on the various criteria as discussed. The flight assignment model will take the list of prioritized purchase orders and the available delivery capacity per week as inputs and determine which orders will be delivered through the available delivery capacity per week. To integrate the two modules, we created a function that takes the output of the PO prioritization module and the available delivery capacity as inputs and returns a list of purchase orders that can be shipped in the current week. The function will call the PO prioritization module to generate the list of prioritized purchased orders. The function will then call the flight assignment module to determine which orders can be delivered through the available delivery capacity. Finally, the function will return the list of purchase orders that can be shipped in the current week. This function can be integrated into a larger system that reads purchase order data, generates priorities for the current week, and assigns available delivery capacity to the prioritized orders. Larger system data can be tested by providing it with a set of purchase order data and checking the output of the system matches the expected output. The system can be tested with different sets of purchase order data to ensure that it can handle different scenarios and provide accurate recommendations. So this is how we're going to deploy our solution so that the use of by UNICEF. The development of a user-friendly software package for vaccine order prioritization would involve multiple modules. The user interface module would be designed to be intuitive, easy to use, and visually appealing. It would allow users to input relevant data, such as purchase orders and delivery schedules, and view the results of the optimization process. The data processing and optimization modules would be responsible for applying the optimization algorithm to the input data and generating a ranked list of recommended vaccine orders. The software would undergo thorough testing to ensure that it is functioning correctly and any issues would be addressed promptly. Regular maintenance and updates would also be necessary to keep the software up to date with the latest optimization algorithms and data input parameters. User feedback would be taken into account to improve the software's usability over time. Ultimately, the software package would be deployed to organizations like UNICEF to assist in the efficient and effective prioritization of vaccine orders.
So we've managed to create a bulleted point list for strengths and weaknesses we think that our model has. For strengths, we have it We believe it prioritizes urgent and important deliveries, and hopefully it will put a priority on the larger scale purchase orders, as we believe these are going to be the most impacted by the restrictions present. We believe it maximizes use of the flight capacity and how we are able to shift certain capacities from one country to another in a global transportation capacity. We believe it can be customized to adjust for changing priorities. If there's someone above our power that we believe has a different viewpoint on where our priority should be, the code should be as simple as changing where they believe the value should be at. It follows a data-driven approach to prioritize vaccine orders based on multiple criteria. It ensures that the limited resources we have, in this case our transportation capacity, is allocated efficiently. We believe our prioritization criteria and our reasoning behind it is sound and comprehensive. We believe the solution is flexible and customizable. Following a specific order being delayed, it is up to the powers that be to bring this into the next week for the set of purchase orders in that week, or to ignore it altogether if they so choose to. And then lastly, the use of AMPL to generate flight plans provides a systematic and optimized way to transport vaccines to their destinations. In terms of weaknesses, though, we have said that the solution relies heavily on data availability and accuracy. Any errors or missing data could lead to suboptimal prioritization in the distribution of the vaccines. In particular, we need the transportation capacity values to be up to date in order to ensure that our model properly is calculating that global transportation capacity. Additionally, if it's for something like the inventory or the coverage present, especially the coverage in this case, if it's inaccurate and that there is a country that has a high priority, but it's not listed as one, it could be prioritized over a country that wouldn't, which in our model is something we're trying to avoid. The prioritization criteria we have, it is based off of our assumptions as a team within that we have been able to create in a 6-week time frame. It may not fully capture the complexities and nuances of the vaccine distribution process in certain contexts. Something that came up in our optimization model itself is actually relatively simple. Something we realized that may be an issue with it is that it doesn't actually penalize delays. Currently, what happens when an order is delayed is that it only increases the priority of it. And while that is a pretty big increase of the priority, it still creates it shows a model that shows wider slashes through data instead of precise cuts. Additionally, the use of AMPL we have, it may require more technical expertise. If someone is to better implement this, they would need a better trained team of programmers to make use of it. It may be less accessible organizations that don't have the resources or the expertise available to us. And lastly, if we're looking specifically at Order 322, there may still be heavy delays of these lower prioritized orders. And if it's a highly prioritized order and our capacity still isn't able to make up for it, and we don't have a way to penalize it being delayed as much, like stated above, it could be heavily delayed throughout the entire year, and that's something that we've recognized.
So to wrap up and kind of draw everything together, we believe our data-driven approach is crucial to reduce the spread of disease. We believe that although we're highly dependent on data, and our prioritization is a little bit subjective, the data-driven and kind of numbers-based approach is what sets our model apart. So overall, I think that our model provides a great basis to expand off of and effectively assigns flights and capacities to our purchase orders.
Overall, I think you should give us 100%, and you should pick our model.
Yes.
Agreed.